video, we are going to look at how do you calculate the growth or decay factor for a different time frame. So what we know is that A, the growth or decay factor, is equal to the Y2 value divided over the Y1 value when the time is changing by 1. And that 1 can be 1 hour, 1 minute, 1 day, 1 month, 1 year, 1 unit of time. And that's excellent, but sometimes we've had data sets where the data given, the time was not changing by 1 unit. And so we need to be able to adjust our A value for either a shorter time or a longer time than what we originally know. So we're starting off with the A, and this is the A in the NPAT formula, which is that growth or decay factor. And so we have A and we have time. And so our original A is figured out by either using Y2 over Y1, or we can use 1 plus R if it's growth, or we can use 1 minus R if it's decay, and we have a word problem. So one of those ways we get an A value. Now, if the time is shorter, we want to figure out what fraction. So if the time is shorter, we're definitely going to use a fraction. And so I want to figure out what fraction of the original. So 1 over n, so it's 1/n as long as given. And so then, because we know that time is the exponent, so over here, because time is the exponent, we'll take our A value that we got from the problem, and we'll take it to a fraction. So if I know time for the year, and I want to know time for a month would be 1/12 as long as a year, so I would do A to the 1/12 because I'm only using 1/12 of the time. Now, if we're working with longer, this is going to be a whole number. And I say that, but it's primarily a whole number. It could actually have a decimal, but primarily a whole number. And this time we would be looking for it to be n times longer. Than what is given. So, and I would take A, and again, because time is the exponent, I would take it to the nth power. So, for example, here, if I figured out A, and I knew A for 1 day, and then I'm like, well, what happens in a week? A week is 7 times longer than a day. So I would use A to the 7th because there were 7 days in a week. So let's try this out with an example problem. So we are told 100 milligrams of the medication has been administered to the patient. So immediately I see this as the start. The package insert explains that most patients will eliminate, so there's that limit, eliminate, this means it's decay, 10% of the medication in their body every 4 hours. So my given time frame is 4 hours. I need to figure out A. I have a percentage, so I know that, and I know it's decay, so A is going to be 1 minus R. So A equals 1 minus 0.1, where 10% is a decimal, is 0.9. So 0.9, 90% remaining, 10% gone, time frame of 4 hours. So then it asks me to figure out the hourly. So hourly would be 1/4 of 4 hours. Because the given time frame was 4 hours, I want 1 hour, that'd be 1/4 of it. So what I do is I take my 0.9 to the 1/4 power, because I only want to know what's going to leave the patient in 1/4 of that original time. And I do that on my calculator, so I get 0.974. Now, sometimes this can feel confusing, but let's think it through. Because it's decay, this 0.9 would tell me at the end of 4 hours, 90% remains. So that's the same as eliminating 10%. So this would be in 4 hours. 90% remains in 4 hours. That's what was given in the problem. Now, my new decay factor, my 0.974, if I change that to a percentage, would say 97.4% remains in 1 hour. And that makes sense that they have more at the end of an hour because their body hasn't been working on this as long as they have not eliminated nearly as much. And so that math construct of using the fraction will help us get a shorter time frame. So if I write the NPAT formula for time in hours, I would have N equals, my p-value was 100. We noted that at the beginning. My A value is 0.974. And my time is, I'm going to use H for hours. You could use T though, and you'd be fine. All right, so now we're thinking daily. So I know a day is 24 hours. Originally, I was given 4 hours, so 4 to 24, I'd have to multiply by 6. So this is 6 times as long. So I take that 6 and I use it as the exponent. So 0.9, 90% remaining or 10% eliminated, but that happens 6 times in order to get up to a day. So I do that on my calculator and I get 0.531. And so if I'm trying to make sense of that, like I did to the others over here to the right, 0.531 is 53.1%. And that's the percent that remains at the 1 day mark, at the 24-hour mark. And I can see that where 90% is there at the end of 4 hours, 53% is there at the end of the day because their body has been working the entire day to eliminate this med, and more of the med is filtered out of their bloodstream and eliminated by the body, and so a smaller percent remains. So they asked me to, again, write a formula. So this would say N is started at 100. My decay factor now is 0.531. And I'm going to use D to denote that my time is now in days. And so I can give the formula for hours, for days, and the original information was giving me just a nice percentage there with 10%, but that was 4 hours worth of work by the body. And so I had to break it down to the 1 hour mark and to the daily mark. One thing to keep in mind is I should always go back and compare to the original, because my 0.974 that I had there for the 1 hour mark is definitely a rounded number. And so if I use that to calculate the daily percentage, I'm going to have some rounding error in that. And so that's why I always want to go back to the given to figure out how many times longer or what fraction of the time is used.